Uh, in this capsule, we'll continue our discussion on the stability of anions. So, in order to do that, we needed to discuss the hybridization, and here is the summary of the hybridization. Different types of hybridization that a carbon atom can form. So it can have sp3, sp2, sp. Different types of hybridization. sp3 carbons form carbon-carbon single bonds. sp2 hybridization will result in C double bond C, and sp results in C double bond C. So I have summarized the important data here, which you can get from other sources as well. But in order to look at the stability of anions and how hybridization will help predict the relative stabilities of the anions, we focus on one key aspect that is shown on this column. So let's look at these three data points. So in an sp3 hybridized orbital, the s orbital contributes 25% to the hybrid. And in the sp2 hybridized orbital, this orbital contributes 33%, just mathematically, and the contribution of the s orbital to the hybrid is 50%. So keep these numbers together, and we'll come back to them. Keep those numbers together, and we'll come back to those. And we will talk about the stability of carbanions. Now, carbanion is an anion where the negative charge is on the carbon. So we have seen in previous videos, negative charge is on different atoms. For example, on oxygen, nitrogen, or fluoride, chloride, fluorine, chlorine, and we use different explanations in each case. So in this video, we are looking at these three anions. So there's one, and then here is the second one, and then you have the third one. Okay, so in this case, you have three different anions, and in each case, the negative charge is on the same atom, the carbon. So what differentiates these carbons? This carbon is an sp3 hybridized carbon, this is an sp2 hybridized carbon, and this is an sp hybridized carbon. So this electrons reside in these orbitals. In this electron on this anion A resides in an sp3 hybridized orbital, and the anion in B resides in a sp2 hybridized orbital, and in this case sp hybridized orbital. So from the previous data point, we noticed that this contribution in an sp3 hybrid orbital is 25%, and this one is 33% as S contribution to the hybridized orbital, and this one is 50%. In other words, we can say that the greater the S contribution to the hybridized orbital, the electrons are that much closer to the nucleus. If an electron is closer to the nucleus, then what will happen? It will be held, there will be more attractive forces. That results in more attractive forces. In other words, those electrons are stabilized because of the nuclear attractive forces between the nucleus and this negative charges. It's just that much, these electrons are that much closer, these electrons are that much closer to the nucleus because the sp hybridized orbital contains 50% S character. And this one is slightly further off, and this one is further off, distance wise. So the attractive forces sort of diminish, which makes this one the most stable anion. So of the three, this particular anion is the most stable, and this one will be the least stable. So here we invoked hybridization to explain the relative stabilities of different anions, carbanions, just another word, carbanions, because the anion is on, the negative charge is on a carbon. In other videos, we'll also talk about carbocations. In case you're wondering, there's something called a carbocation as well. We'll not touch that yet. We'll come to that. So this is another concept we utilize to explain the relative stabilities. So all this, we need to keep all these things together. So I have all of them titled factors that impact the stability of anions. So we stop here. There's one more, and then we'll finish all the different factors that help predict the relative stabilities of anions. So we stop here.